Welcome to the first part of Unit 12. In this unit, we're going to introduce the concepts of impulse and momentum. And to begin that discussion, I'm going to remind you of Newton's second law. So remember, Newton's second law is the one that said that the net force on an object equaled the object's mass multiplied by its acceleration. And what I'm going to do is I'm just going to manipulate this statement. And the first thing I'm going to do is I'm going to plug in the definition of acceleration that we had way back. I think in Unit 2 is where we first met this definition, that acceleration was a change in velocity over change in time. So if we plug that in, we get that the net force is the mass multiplied by the change in velocity divided by the change in time. And now what I'm going to do is I'm just going to rearrange this a little bit. And on one side, I'm going to take the net force and multiply it by the time interval. And on the other side, I'm going to have mass times the change in velocity. Okay. And this is the introduction of our two principles. Both sides of this statement, by definition, equal the impulse. Sometimes you'll see this written as a capital I with an arrow over it because it is a vector. Sometimes you'll see it written out as the full word. On the equation sheet, for space reasons, I did use the capital I. Okay. So impulse has two definitions. It's net force multiplied by a time interval, and the other definition is mass times the change in velocity. This is very similar to the definition we had for work in the last couple units, where work was a force times a distance, or it was a change in energy. So the first thing I'm going to focus on is this portion of the impulse equation, mass times the change in velocity. And what I'm going to do is I'm going to make a definition. And that definition is the linear momentum. The linear momentum is given by the letter P. You can see I bolded it here to make sure you understood it was a vector. I have it written down here that it's a vector. I have a bolded V there to make sure it's a vector, and I've added arrows. It's a vector. Okay, so linear momentum is by definition P equals mv. So on the last slide, we had m times delta v. That would be mv final minus mv initial, which is the final momentum minus the initial momentum. Okay. Now you may be wondering, why do they use the letter P for momentum? M is taken. Capital M, lowercase m. M is taken. It means mass. And we don't want to get confused here between something that is a mass and something that involves mass. For example, an equation that looked like this would be no end of confusing. So we're not even going to go there. Okay, so M is taken. We can't use M for momentum. So I don't know how they came up with P. What I like to think is they said, okay, M is taken, and then they just started going through the alphabet. Could we use N? Well, we could use N, but N is already used for normal force, and M and N are very similar, and Okay, well, what about O? Well, O is very similar to the number 0. Let's skip O. P. Is anybody using the letter P? Let's use it. There we go. The units of momentum are the kilogram times the meter divided by second. Unlike force and energy, this one does not have a name. No fancy name here. It's just kilograms times meters divided by seconds. Okay, so now if we return to our definition of impulse, so impulse, let that be capital I with a vector. Remember, it had two definitions on the last slide, F net times delta t, which was m delta v. I can now rewrite this instead of as m delta v, I can rewrite it as a change in momentum, a delta p, as we saw on the last slide. Okay, so impulse is net force times time. It is also change in momentum. Now let's think about this a little bit. What applications do we have for impulse? So the first thing I want you to think about is a car. Modern day cars are designed to crumple upon impact, which is why when you get into a, what seems like a very, very minor fender bender, you have thousands of dollars worth of repairs to do. That's a choice. So what we have is, for example, we have a car driving down the road at some velocity v, and then something happens, and let's say the car has an unfortunate impact with a tree. For this, the change in momentum is fixed. The change in momentum is fixed by how fast were you going to begin with and the fact that you stopped. Nothing's going to change that. But if we look at the other definition of impulse, so remember, impulse is net force times time, which equals delta p. Okay. This, it's fixed. It's based on what's going on with the collision, the situation at hand. But it's in everybody's best interest if the net force on the person inside this car is as small as possible, to make the chance of this person escaping with as minimal injuries as possible very likely. If this is fixed, then to make the net force small, what I want to do is I want to make this big to make that small. Well, how do I make the time of impact big? Well, I extend what can happen. If what I'm doing is running a nice hard piece of steel into a tree, well, then the time of impact is going to be very, very short, because that steel is not going to bend, it's not going to give, it's steel. It's not doing anything. On the other hand, if I design whatever is hitting the tree such that it folds and it crumples, that process of folding and crumpling is going to take longer than a sharp impact like a piece of steel would have. So I extend the time, therefore I decrease the net force and make it more likely that the person inside is going to come out uninjured. Another good application of the concept of impulse is an egg drop contest. So remember, the point of an egg drop contest is you start at some height and you come down to the ground and you put the egg in and you want it to survive the impact. Okay. Just as we saw with the car example, the change in momentum here is going to be fixed. Okay, so remember, change in momentum is going to be mass times the change in velocity. Well, when it hits the ground, velocity has to go to 0. How fast is it moving right before it hits the ground? Well, that we can determine by conservation of energy. Our initial energy is going to be mgh, gravitational potential. Our final energy will be kinetic, 1/2 mv squared, right before it hits the ground. Okay, and letting initial energy equal final energy gives us v is the square root of 2gh. So the speed right before it hits the ground is going to be given by the square root of 2gh. After it hits the ground, the velocity will be 0. And that's the same regardless of what's going on with the egg. But I want the egg again to survive. I want it to have as small and a force on it as possible. So now I come over to this combination. Net force times time has to equal my change in momentum. Well, if the change in momentum is constant based on how high I'm dropping that egg from, then I want to increase the amount of time it takes for the egg to come to a stop such that the net force on the egg is decreased. Now, think about egg drop contests. How do you design something for an egg drop contest? You do things like you put pillows around the eggs, right? What do pillows do? Well, they're soft and they're malleable and they don't just crash into the ground. They kind of, more gently land. They fluff onto the ground. I don't know if that makes sense. But you add pillows, you add cushions, you do all these sorts of things. And the whole point of all those sorts of things that you do to make your egg survive is to extend the time of impact. A similar discussion could be had for an egg toss competition. So remember, in an egg toss competition, it's you and a friend, and each time you successfully toss the egg back and forth between each other, you take a step back, making the distance you have to toss longer. And the best way to keep from breaking the egg is when the egg comes at you, rather than holding your hand still, you move your hand with the egg so that it more gently comes to a stop, extending the time to decrease the force for the same change in momentum. In the next section, we're going to do a bunch of examples involving impulse and change in momentum.